Okay, so we've calculated now the electric field due to three charges, but there's another concept called as the voltage or the electric potential. And so, in a sense, you can think of this as that in analogy to how we calculate an electric field, where then all we needed to do was to then multiply by the some charge that we're going to put in that place, and that tells us the force on that charge. We can also basically calculate the electric potential or the voltage at any point, and then we can multiply by some test charge that we'd like to put in that location, and it will actually tell us the amount of energy that we have. So classic example is that if I had a situation where I have some charge configuration like we had in the previous problem, and I asked basically how much energy would it cost for me to bring this charge in, or if it actually is an attractive situation, then you might say how much has this thing sped up by, basically how much kinetic energy has it gained in the process of coming toward this charge configuration here. So just to stay kind of consistent with the last problem, since we already have kind of the numbers and the geometry kind of matched up, so we used this number 0.4 meters between here and here, and we used a 3, 4, 5 triangle concept here to say that this is actually 0.5 meters, that this here is also 0.5 meters. Now, the cool thing about calculating voltage is that we don't actually need to use vectors. We can actually just simply write that the voltage contribution from each charge is just equals to the voltage is going to be K times Q1 over R1. And so, for example, we can also generalize this, that if we wanted to compute the voltage from multiple charges here, we can say that the V total or so is going to be equal to the sum of KQI over Ri, and we'll sum over all the charges. So let's try so this is just for if you wanted the voltage around a single charge, and this is going to be the voltage around many charges. So actually, when I'm starting to try to visualize these things and have it make sense, I use a simulation called the PhET simulation. This is the physics education team, and you can look up charges and fields. And if you look up charges and fields on your favorite search engine, in PhET, P-H-E-T, you will find a simulation that's actually very helpful, that it will give you this sense of this 1 over r business here. If I were to have a positive charge in some space, then if I look at r, the distance away from this thing here, then the potential looks something like this. So it's basically like, I don't know, I like to think of it as maybe kind of like a hill, like a volcano type of thing, but without any, which kind of comes to a kind of infinite point. So as close as you get to this thing, this potential will keep rising. But the point is that if I try to bring in another charge in here, I'm going to have to climb up that hill. And as I want to get closer, then I have to essentially I have to overcome more of that voltage. In other words, if I had a positive charge that I was trying to bring in closer, I would have to overcome more potential energy, just like how in your mechanics course you saw that if you wanted to climb a hill, you need to pay an energy, mgh, in order to climb up some hill of a height h. So let's just calculate, and then we'll talk about the result here. So again, I'm going to just calculate my total voltage at this location here that I'm interested in. And so I'll add up the voltage from Q1. So this is going to be K times Q1 over R1. And I'm going to add up K times Q2 over R2 and K times Q3 over R3. It seems kind of boring, right? We don't have to worry about all those vectors anymore. In fact, this charge could be anywhere in a circle around this thing, and we would still have exactly the same result. We'd still have exactly the same voltage at that point. So, so let's calculate this here. We'll just put in the numbers here. So we'll have 9 times 10 to the 9. That's newtons, coulomb squared per meter squared. And then we're going to multiply by the first charge over its distance. Notice it's over its distance, not its distance squared. And so we'll have the, let's see, 2 microcoulomb divided by the distance, 0.5. And then we'll add this to the contribution from the second charge. Gosh, it looks like it's actually the same. It's 2 times 10 to the minus 6 divided by 0.5. And then we'll add the contribution of the third charge, which looks to be a minus 4 microcoulomb divided by 0.4 meters. So that's our total contribution here. And now we'll just pause the video for a moment so that I can plug these numbers into my calculator and we can compare results. Okay, so I've plugged in my numbers into the calculator, and I see here that the contribution from these first two terms gives me this number here, which we'll then multiply by k, and then we'll get a minus term from the third term here. When we plug in all these numbers together, we find that we get a minus sign overall because of the dominating term of this minus term here. We get minus 18,000 volts, or minus 18 kilovolts. We can actually think about this as this is the amount of energy per charge that we would actually have to give in order to bring a charge into the configuration. But now, because it's a minus sign, what does it mean to have a minus energy? So here, I think about the fact that actually it's like I'm going downhill. So for example, it would be like I started at this location and I went down. This would be going to a lower potential energy. So you could think of this as that if a positive charge were to come from some faraway place and start coming toward this configuration of these three charges here, it would overall see kind of a downhill slope. And so it would overall be going downhill to this point, which means that we could actually figure out how much, for example, potential energy it would say pick up. So a classic kind of application of this kind of thing is to say, okay, so remember that 2 microcoulomb test charge that we were talking about? So what if I brought in a Q, let's say Q is equal to 2 microcoulomb, and let's say I wanted to bring it in from far away. So I could actually say that the work that I did is equal to this voltage, which is the energy per charge, times this Q. And so in other words, that this minus 18,000 volts times this charge here, 2 times 10 to the minus 6 coulombs, it turns out that a volt times a coulomb is actually a joule. And so this would be a minus 0.036 joules. So this means that I would actually pick up this much. So doing a negative work on something to bring it to a place, it kind of is like saying that you get it for free. In other words, that you didn't have to do any work. You actually gained energy by the fact that this charge moved from some faraway place into here. And so, for example, one application might be is you might ask, well, if the charge started far away and it wasn't moving at all, then by the time it got to this point here, how fast was it going? And so you could actually set that 0.036 joules, you could set that equal to a half mv squared, for example. And if you knew the mass of that particle, you could solve for the velocity, for example. Another example is that if I had a negative charge, then I would have a minus and a minus, and there would be a positive amount of work that I would have to do in order to bring that charge in to this particular point in this configuration. So hopefully that is starting to make some sense, and you're understanding now how you can calculate potentials, as well as the discussion that we had about how you calculate electric fields. Please visit the PhET simulation for charges and fields, and it will help you to build some intuition about what these voltages and electric fields are really looking like. Thank you.